We'll now restart with 4 oral presentations for the next hour. The first presentation will be by Andrew Wu from Amherst. His presentation is titled Lemur, Integrating Large Language Models and Automated Program Verification.
Thank you for the introduction. Hi, everyone. I'm Andrew. I'm an assistant professor at Amherst College, and this work was conducted during an internship last year at VMware Research. So a bit of a motivation of this work. So large language model, as we all know, has demonstrated tremendous ability to understand programs. I'm sure we have all used it to perform various programming tasks, for example, from natural language to code, from natural language to SQL, or to formal language like constraints. Recently, it has also been shown that large language models can also generate program invariants, demonstrating deep understanding of computer programs. So there was this ICML paper 2 years ago that posed this question and showed some promising initial results. So the initial part of our work, we conducted some experiment just playing with large language model and test their ability to understand program and generate program invariants. So here is a very simple program. It has 2 variables, x and y. And it's kind of a trivial play, a toy program. It has an infinite loop. And what it does is that it will just keep adding y to x and adding 4 to y. And the assertion in this case is that x is not equal to 30. So even though there are overflow issues, this assertion should still hold. Hopefully we can all see that. Right. So and then the query that we asked large language model is that print looping invariants that help prove the assertion, as the assertions don't explain. So here we want to actually try to prove that this assertion holds. So this is the part of the output of GPT. So we can see that it does some annotation of the program. Right? It outputs some reasonable invariants. For example, the first 2, that it says y modulo 4 should be 0, and also x modulo 4 should also be 0. So these 2 are correct invariants. And in particular, the second one, x modulo 4 is equal to 0, indeed, it then should imply the property, right? Because if the assertion is true, which it is in this case, then we can derive that the assertion holds. But the last one, it's incorrect, right? For example, x less than 30, that's not true in general. So what we found is that GPT can generate insightful looping invariants using operators not even in this program. For example, modulo is not in this program, so here we're contrasting with, say, more traditional invariant generation techniques, where it's often we would look at what's already there in the program and try to come up with some invariants. So this is a promising observation, but obviously there are cases where incorrect invariants, or in this case, basically invalid invariants, are generated, right? So nonetheless, it's a promising observation, and so. To summarize our finding or our initial hypothesis, large language models as invariant generators, it has some advantages, right? Compared with existing learning-based invariant generators, LLM, it does not require domain-specific learning, though it might help, but it's already trained. It's a product that can be used. And it can also process programs of various forms. So we are contrasting this with, for example, more earlier work on learning to generate programming invariant, where the invariant generator is trained to handle programs of a very specific form, right? But in this case, large language model does not have this problem. So based on these observations, we asked this question: can we leverage LLM's code understanding ability for automated program verification? So this is a task that is a challenging, ongoing problem that the formal methods community are trying to tackle, right? Part of the reason is that we have automated reasoning tools that can perform low-level logical reasoning, but sometimes to prove that a program is correct, we actually need more high-level understanding of the program that can guide the verifier to perform low-level logical reasoning. But there are some practical challenges with this. First, we need prompt engineering, right? GPT output can be messy and hard to automatically process. So how to kind of provide an interface of GPT or a large language model with a formal verifier, that's a challenge. And the second, perhaps more interesting challenge is that large language models, they're only suggestions, and the output can certainly be wrong, right? And what do I mean by wrong? So in this case, it can simply not hold. It's a false assertion in the program. Or it is an assertion or the second case is that it is an assertion and is correct, but it does not really help to prove the proof goal, right? So if true is a correct assertion, but it doesn't really help. So our key observation here is that we want to kind of decouple this task of verification. We want to use formal verifier to guide the large language model in this case, and we want to create a process that integrates tightly these two, where the verifier would be checking the correctness and the implication of the assertion provided by large language models. So on the high level, this procedure that we foresee, it takes in and input a program and an assertion that we want to prove, and the output is whether the property holds or not. So in this case, large language model, it can be used to suggest proof goals. It can be used to strengthen proof goals. It can also perhaps repair the proof goals. And the program verifier, it would check implication. It would check proof goals, and it would also provide feedback. So if the proof goal suggested by large language model turns out to be incorrect, this feedback should be given by the program verifier to the language model, and the language model can potentially use that to repair. So this is a high-level idea, and we actually formalize this as a formal calculus. So we don't have time to get into the detail of this calculus, but the point here is that this is a calculus where we have interactions between the oracle, which is a large language model, and a verifier. So the oracle's job, the language model's job, is to propose potential proof goals for the verifiers to first verify and then to check implication. And then we also have a lot of verifier calls that checks the correctness and implication of the proposal by the large language model. And we have termination conditions where success 1 and success 2 denotes two conditions where we can conclude that the original property holds on the program. And we also have fail rule where a counterexample is found. So what I want to show is some example traces of how this proof procedure works in practice. So let's say we have this simple program. It's, again, a while loop where we keep adding 4 to this variable x, and we want to prove that x is not equal to 30. So perhaps it's a little bit surprising, but actually half of the tools that participated in software verification competition in 2023 cannot solve this problem. And part of the reason is that it's very obvious to human eye that this assertion should hold, but it turns out that coming up with an invariant is hard because, for example, the invariant in this case, it's x modulo 4 is equal to 0. That's a very helpful invariant, but it does not. This modulo operator is not in the program, right? So it's hard for automated reasoning tool to guess that modulo might be useful. But it's not a challenge for a language model, as it turned out in this case. But we still need to handle the case where what if the proposal is incorrect, right? So this is the procedure that I want to show. So let's say we have this original program. It has an assertion that the verifier needs to prove, and the verifier returns unknown. So what we would then proceed to do is we would call large language model to propose a sub-proof goal. So let's say the language model produce something like this. So this assume is essentially the proposal that language model provide. So in this case, let's say it proposed something like s modulo 2 is equal to 0, a reasonable proposal. But it doesn't really directly imply the property, right? It's x modulo 2 equals 0. It doesn't mean x cannot be equal to 30. So let's say the verifier returns unknown again. So in this case, we could invoke the repair rule, where it basically says the verifier, returns unknown, try to strengthen this proposal. And let's say in this case, it gets it right. So now the verifier would return true. So the true here says is essentially representing the fact that the assumption implies the assertion. But we're not done yet, right? So what happens now is that we can apply another proof rule that would precede our proof. And the proof now is actually, we need to actually show that x modulo 4 is equal to 0. So this is our new proof goal. And we can invoke the verifier again in this case. And this would be an easier property to prove because it's inductive. So in practice, and we also observed that, the verifier is able to handle this assertion. So let's say in this case the verifier does, and so we're done. We can apply the success rule. And what about an alternative universe? Because we all know language model output can have stochasticity, right? So let's see an alternative case where it just proposed something that's wrong. In this case, the verifier would actually return true, because if you start with a false assumption, you can derive anything, right? So in this case, we would apply the decide rule, and it's going to say, okay, this is our new proof goal now. But in this case, the verifier is going to actually derive that this property does not hold, because the counterexample can be easily found. In this case, we would apply the backtrack rule when the verifier says, okay, the current one is incorrect. And then perhaps we would, the backtrack rule would invoke the language model to do another proposal. And let's say it gets it right. So as it go, right? So this is the procedure that we designed. We implemented a terminating procedure on top of this proof system. And we perform an experimental evaluation. So this implementation, it has 1,500 lines of Python code. We use GPT families model. And we selected 2 verifiers, state-of-the-art program verifiers. And we focused on 47 short C verification benchmarks from the SVComp 2023. And so those are problems that cannot be solved by those 2 baseline solvers in 10 minutes. And we considered a bunch of configurations. So there are the 2 baseline solvers. And we also have the procedure where the verifiers are implemented as ESBMC and UOptimizer, and the large language model or the Oracle are instantiated with GPT 3.5 and GPT 4. We use a 15 minutes timeout on those benchmarks, and here are the results. So as we can see, even if given a slightly more time, the baseline verifiers cannot verify a lot of problems. But with the augmentation of the language model, it's able to solve a lot more. And with GPT-4, it's able to solve over half of the benchmarks. So here is the initial result that I want to show. And the conclusion of this work is that language models, they're able to assist formal verification. And our results are just initial steps. And what we saw at that point was that GPT-4 really outperformed GPT-3 in this case significantly, right? And so our suspicion is that if we use even newer, more advanced model, it's going to lead to better verification performance. Thank you for your attention.
We have time for one quick question. Yes? Is there a microphone?
Do you have any kind of, proof that your formal procedure has some guarantees or is correct in some sense.
Yeah, indeed. So the good thing about this, the involvement of a verifier is that we can actually prove that the procedure, if we derive a state where the success rule can be applied, then the property actually holds. So we have the proof in our paper. So the calculus is sound. So that's the theorem in our paper.
So then the limitations come from the power of the language model?
The limitation, yeah. So let's say the language model gives incorrect or not useful invariant or proposals, then the procedure is just not going to terminate. And the limitation can actually also come from verifier. We do observe that. Like sometimes we see that the language model provides a really insightful proposal, but the verifier cannot handle it. So like what we see here is that this entire verification success rate can improve. It really comes from improvement in both language model and in the verifier.
Thank you so much for a great
Thank you.
presentation.